Good afternoon, ladies and gentlemen. So today is graphs. Again, 3 lectures. When we refer to the word graph, in this context, we do not refer to something that you use in mathematics or statistics or physics. Graphs with an X and Y axis, numbers on it. So it is another context, same word. A graph is also, as a linked list or a tree, a structure with nodes. And on the nodes, we save data. And then the nodes are linked in some or other way. So the only way in which the nodes are, in which the graph is different from the other structures is the way in which the nodes are linked. With a linear structure, the nodes are linked one after the other sequentially. With a tree, the nodes are linked starting with the root, and then we have children and subchildren, etc., grandchildren and great-grandchildren. And then with a graph, we have nodes, and then we can link them with edges as before. Let's go to another, maybe more simple example first, and then we will, So that's a diagram of a typical graph. That's a typical graph, and the nodes are linked with edges. In this case, the nodes are also the indexes. It's not always the case, but here in this example, the nodes are the indexes, so they are starting from 0, 1, 2, 3, 4, 5, 6. Yes. In a real world example, we can have a map. So this is a graph. A typical road map is a graph. The towns will be the nodes, also referred to as vertices. And then the roads between the towns will be the edges. So that's a real world example of a graph. Another example would be a network topology where you have routers and things that are connected with network cables. So nodes and links between them. My wife showed me this picture earlier this week, and I said I must show it to the students because this is also a good example of a graph. So that's the river system of South Africa, Southern Africa. You will not see Caledon, you will not see Vaal River, etc., and Modder River. You will not see them because they are part of the Orange system. All of those eventually run into the Orange River. So the whole Orange system is all colored in white. And then you see the other river systems colored in other colors, and they are not connected to the orange, and that is because that is where the escarp runs. The top of the mountains. So the Drakensberg runs down there. Then everything this way goes to the Atlantic, and everything this way goes to the Indian. And then so they're not connected, the orange with the other systems. So that's your arteries in your body, flowing blood is also graph. In this case, where we have now these different separate river systems, we refer to the graph as unconnected. So there are nodes. Let's call the nodes all the places, the conjunctions where the rivers join. You have the Caledon and the Orange River joining near Betuli in what's the place name, Tussen die Riviere. And then you have the Vaal River and the Orange River joining 10 kilometers downstream from Douglas. So let's call those conjunctions the vertices. And then the places, the parts of the river between the conjunctions will be the edges. So that's a typical graph. There are many examples of graphs in life, in real world. So we can put weights on the edges. So a weight will, in this case, be the distance. From Bloemfontein to Botshabelo is 70 kilometers. Now, these distances that I have there in red, they are more or less, but they're not exact. I put more or less distances there, but I did not do it exact for the sake of simplicity, because I think from Bloemfontein to Botshabelo is less than 70, 63 or something. All right. So those numbers in the red, they are the edges, the weights rather, they are the weights. So we can now travel from Bloemfontein to Maseru and add the weights. We can put all together. So 70 plus 10 plus 15 plus 70 plus 20 will give you whatever, 140, 150, 171, what's it, 185, if I am correct, from Bloemfontein to Maseru. If we have lockdown and the border at Maseru Bridge is closed, and also between Webner and Mafeking, then we will again have an unconnected graph, two separate road systems are not connected. As it is here, it's connected. We can't travel from Bloemfontein to Maseru. We can, unlike a tree, we can travel in both directions of an edge. We can travel from Bloemfontein to Botshabelo and back from Botshabelo to Bloemfontein. No problem. So it is possible to travel in both directions, unlike in a tree. In a graph also, there are cycles. You can travel Bloemfontein, Reddersburg to Wetstorp, Bloemfontein in a cycle. So you end where you start. And then there are paths, multiple paths between two vertices possible. If I want to travel from Bloemfontein to Maseru, let's get my pointer. If I want to travel from Bloemfontein to Maseru, there I can go the Westorp Webner Hobbyhouse, Lady Brand Maseru. I can, if I want to. I can go Reddersburg, Smithfield, Webner, maybe Zastron, then Malizoek, Mafeking, etc., Maseru. So the possibilities are endless. I can even do the following. From Bloemfontein, travel with the N1 to Cape Town, and then follow the N2 to Durban, and then go to Maseru via Sani Pass, if I want to. So there's really unlimited number of possibilities. So one of the most important challenges or usages of a graph is that of finding the shortest path. Now in a small graph, with limited number of vertices and a limited number of edges, I can do a brute force. I can list all paths from A to B and then iterate through them and find the shortest one. But as I have just indicated, it is not always possible to do that brute force because there are unlimited number of possible routes from an origin to a destination. So there are several algorithms. One of the most well-known mathematicians, computer scientists in history is that of Dijkstra, a Dutch person, who developed the shortest path algorithm for graphs, finding the shortest path between two nodes without having to iterate through all possible paths. And we will get to that possibility later. So I want us to understand basically the idea of graphs before we carry on. So we have to understand the basics of graphs. Terminology, I refer to vertices, vertices that are connected or adjacent. I refer to a path, that's a set of vertices, the one following the other, from a specific origin to a destination. The length of the path, note that is the number of edges. That is not the sum of the weights. Don't confuse. The length of a path is the number of edges. It's not the sum of the weights. And I can weight paths in terms of their distances. The shortest path will be the one with the smallest cost or the smallest total weight. I refer to loops. Here's an example of a directed and undirected graph. And we know that Nelson Mandela Avenue and Zastron Street are oppositely directed. If we start from Mimosa, we have one-way streets. So, in other words, you cannot travel the other way. We can refer to a vertex or a node's successors or predecessors. So, every node that is adjacent to a specific node, meaning I can travel from one node to the other, will be referred to as its successors. So if I have a look at node 1, and note the loop between 1 and itself, you can travel from Bloemfontein to Bloemfontein, but just taking a small loop to the countryside. So the successors of 1 is 1, 2, and 6. The successors of 2 is 1 and 6 and 4. Got it? All the nodes that are connected. Predecessors, it depends on whether the nodes are, whether the edges are directed or undirected. The predecessors of 2 is exactly the same as its successors if all edges are undirected. But if some of the edges are directed, then the predecessors and the successors are not the same. So we have to understand that, successors, and we are going to have a lot of work and in the code with successors. So we need to understand the idea of successors. Let's go back there. Shortest path, weighted, loop, successors, directed, undirected. Connected and unconnected. Those are when if I have a look at this, no, not this example. Let's have a look at the next picture. It's somewhere, there's one. So there's a picture of some nodes that are not connected. So I cannot get to node number 5 if I start with number 0 or any other one. I cannot get to 5. If I start with 1, I cannot get to 0 and 4 also. 0 and 4 also forms an island. So it's not always that all vertices are connected. All right, so we have to understand the idea of connected and unconnected graphs. Let's go back to the terminology. What did I skip? All right. The next important thing is that we have to understand now how do we implement, how do we model a graph in a program. So there are more than one possible model. List of successors, list of vertices, an adjacency matrix, list of edges. There are more than one possible way of modeling a graph in a program. And we will discuss them one at a time, starting with the easiest one, the list of successors, and then going on to the others. I will hope to finish list of successors today, and then also start with the list of vertices, but I will not finish list of vertices today. If you have a look in the left-hand side where we have the navigation panel, the list of successors is there. Those are the subtopics, and then list of vertices, and there's quite a lot of subtopics there. This entire chapter is, 34 pages. So it's quite a long chapter. And I warn you, it is here and there maybe a bit challenging. All right, so yeah. And your last project for the semester will be on graphs. And if you need one to complete the 7, you might struggle. Okay. Hope that you have 7 already, because the last one might be the most challenging of the semester. Okay. Many of you did not submit this project 10, the last one. There were only 30. Now, I got 3 people who sent me an email and apologizing for having a workload problem. And I quite understand that. And all 3 of those were people who already had the 7 filled up. But they just sent me an email out of courtesy. And I really, really appreciate it. Just about 30 others who did not submit without notifying me at all. All right, as a list of successors, let's go to the example. Let's go to the example. I have, again, as always, my class that I use for testing. And I built here a graph, and the one that I built in this example is this graph here. And then I have the graph class. And this graph class, as you will immediately notice, and you should immediately notice, is not generic. It is not generic. In this list of successors implementation, we are only interested in the sequence of nodes and the connection between nodes. We are not interested in saving values on the nodes. So it's a very special case. Limited, but it serves the purpose of explaining where we are going with graphs. So it's not generic. Again, in project 10, there were people who put a C car between angular brackets in class. Please don't. It should be generic. Otherwise, we miss the purpose. All right, this one is not generic. So what we have as is a private list of int array. Note that this thing is 2-dimensional. We have an array of lists. And don't confuse array of lists with list of array. I just put this one here in line 15 to distinguish between line 12 and line 15 and look at the difference between them. We're not going to use nodes 2. That's just for the sake of the example to indicate the difference between them. The one is a list of array, the other one is an array of lists. What's the difference? So for this, and of course you can use a list of a list, you can use an array of an array, you can use any one of the combinations when we implement. It's up to you. In this example though, I use an array of lists, line 12. So note it is 2-dimensional. So what we have is an array. Let's start off with the array. So every node in my graph is a member of the array. All right? Every node in the graph is a member of the array. And then every node itself has some successors, nodes that can go from him. And those will be added to a list. Got it? So every node is an array, member of the array. And then within that specific node, we can have a list of successors. So that's why it's 2-dimensional. So the whole implementation of this graph is something that says we go with an array of lists. All right, then we have 2 constructors as before. A simple, easy one, and maybe not so easy one. The simple one, we just specify the size of the array. That will be the number of nodes in the graph. And we instantiate this array, as always, we instantiate with a size between square brackets, and this is an array of a list of ints. And then each one of these lists must be instantiated. So we create a new list for each one of the members in the graph. So we run through the array from 0 to less than size, and we instantiate a list for each one of those. So that is the first constructor. Second one, we leave the work to the class user. So the class user has to do all the work, and then we just send through this already done array of lists we send through to the graph. When we go to the class user, we say, let's go create graph 1. That is create graph 1. First of all, this is calling the first constructor, the simpler one. We specify the size of the graph. And then we use this method, add successor, where we say, all right, add a successor from 0 to 4, from 1 to 1, from 1 to 2, and from 1 to 6. And while we're doing this, we can just as well keep this picture open. Can I try to do this one, put it at the side? Can close that. Can close that one. All right. Got it. So we add the successors. From 0 to 4, there was another one from 0 to 5, which I commented out just for the example's sake. From 1 to 1, that's that little loopy there. From 1 to 2, and from 1 to 6 there. And so we carry on. So we create the graph with size 7, meaning 7 separate nodes, and then thereafter we add the successors one by one by calling this add successor method. For the other version of the constructor, the class user now has a little bit of more work and more understanding to do. This is a recursive thing. So we create the list, and inside, create the array, and inside the array we create a list for each one of the nodes. So if we go to the first one and we go to add successor, let's have a look at how it works. It's as simple as that. We have two parameters, u and v, and these are conventions. Please keep with the conventions, and there's a separate section later on in the chapter specifically on conventions. U and v, then uppercase U and v, and then U underscore and v underscore, and we use these three different conventions for three different things. Here we refer to U and v lowercase. The U is the index in the array of the specific node. The V is the index of all the elements in the graph that we want to add as a successor. So all that we have here is to take the index in the array, nodes U, whatever it is, and that will then be a list, and then add to it element V. Got it? That's simple. To add a successor. To remove a successor, we just use the remove method from the generic list. These lists, they are generic. That's from the .NET lists. So the methods that are available in the .NET lists are also available for us here. So we just use the add and remove, because this thing is an array, but that thing is a list. Got it? This is an array, but this one is a list. Okay? And then we can have a bool has successor. Is there, in other words, a successor from U to V? And we can use the list method contains to do that. We can use a get successor, which will return an array of nodes. So get all the successors of this index V, and that will return a list. And it will return a list like that. So it will return a list of successors. We can list all the nodes, and this is a typical simple depth first structure, and we should take again those two methods in conjunction. The public one, that's being read from the client, and the private one that's being called from the public one. So that's a recursive depth first structure. So the list all nodes method in line 57 is called from the class. That will create a new list, empty list. And then it will call traverse DFT in line 67. And traverse DFT will in turn call itself when needed. There are two important changes from trees that we can notice here. First of all, in trees, you did not have that line of code there. And actually, if our graph is connected, meaning all nodes are connected, we don't need that for graphs as well. We need that line if the graph is unconnected. So that's the one change from the DFT for trees. And then there's another change, and this is this line of code there, line 69. And we need that because in a tree, you start at the root and you go down, you can't get back. There cannot be cycles. You cannot have other possibilities of going to a specific node. There's only one path. From root to a specific node, there's only one path. But in a graph, it's different. There are more than one path from wherever we start to wherever we want to get. And in order to not duplicate nodes in the list, we have to have that if statement in line 69. In other words, it says, if not, my list contains this node, then I can add it. But if it's there already, then just ignore it. Because if it's there already, it meant that I have already added it via another path. Okay. So that is extra. Those two lines of code, 61 and 69. 69 always extra. 61 extra when the graph is unconnected. In other words, when there are separate islands of nodes in the graph. Now this is the discussion of an implementation through a list of successors. I can stop here and ask if there are any questions. All right, so let's carry on with the next section. If I go to view navigation pane again. So the next one is the implementation as a list of vertices. So that's another implementation, another way of implementing my graph. In the previous example, I said that it's very simple since we do not carry the node, it does not carry an extra value. All that we have in the previous example is the indexes. We don't have values on the nodes, but that's not always very useful. So if I have a graph like this one, and that is my simplified roadmap with towns, and I want to save the name of the town on the node. It's a string. It's not an index. Then I have to adjust my previous implementation a bit. And what we do, we have an embedded node class. And by now we are quite aware what embedded classes are. So an embedded node class inside it. So there's my graph class, and now it's generic. Note that, and it must stay generic. You may never change the method inside it to be something with some other class. It must always stay generic. Got it? Okay, so that class is now generic. I can put now anything in it. If I want to put a string in it, it's okay. If I want to put an int in it, it's okay. If I want to put a C student in it, it's okay. Or a C car, or a C hotel, or C whatever. It must stay generic. And then inside it, starting at line 10, ending at line 27, I have an embedded class, a class inside the outer class. That class is private because it's only known inside my outer class. And that embedded inner class now contains the value that I actually want to save, and that value is of type T. That's the thing I actually want to save. Then it contains my list of successors, and this is optional. I can have a parallel array of weights. Parallel meaning same index referring to same thing. So successors and weights are parallel. All right. We again have a two-dimensional structure. It's not much different from the previous one. It's again two-dimensional. But instead of having an array of a list or a list of an array, we have array, was this case, I can't remember if it's an array or a list. I think it's a list. That's an array, line 30. In this case, I have an array of nodes, one-dimensional. And then inside my nodes, I have, in this case, a list of successors, line 13. So it's just separated, right? Still two-dimensional, but the two dimensions are now separated. I have a list of nodes, or an array of nodes. And then within every element in that array, I have the list of successors in line 13. It's still two-dimensional, but it's separated. I think this is actually easier to understand. We don't have now to determine now with what index are we working now. They are separated, so it makes it for easier understanding, I think. So we have an embedded node. Don't confuse the node constructor with a graph constructor. So the node, when I create a new node, I have to assign its value, instantiate the list of successors, and instantiate the list of weights. The graph constructor, I instantiate the array of nodes. Initially, I start with 0 nodes, so I have a 0 between square brackets. Remember previously when we had a static list, we said, all right, you instantiate with, let's say, 2 elements, and then we double the size as needed. You can do the same here. Start off with an initial number of nodes, and then as we add nodes, we just adjust that number. So what I've done here is to start with 0, and then as I add, I resize my array. I can double it, or I can just resize it by adding one spot in the array. So note the difference between the two constructors. To add a node, let's focus on that first. How do I add a node? I have a helper method getNode. Where's my getNode? There we are. Since I have nodes and values, and we said previously, and I think I gave you an example or a hint rather in project 10 of how to get a list of values if we have a list of nodes. The values are encapsulated inside the nodes. And if I have a value and I want to get the node, I go through that part, this one here. So I just run through all the nodes, check if the value equals the one that I'm looking for, and if so, return the node. So make sure that we understand the difference between the values, which is of type T, and the nodes, which is of type node. And nodes contain values. So previously, in the previous example in project 10 with the trees, I said distinguish between T and 3T. Okay? And the list of T and the list of 3T. You got it? So here we have the same thing. Distinguish between the element itself, which is of type T, and then the node which contains that element value. So if I want to get from the one to the other, I need that helper method, line 79. If I want to get the node, if I have the value available. So let's go back to my add node method. I want to add a value, T, but in order to add a value, I need to add a node. So first of all, we make sure that we don't have duplicates. You cannot have 2 towns with the name Bloemfontein. I know there's a Bethlehem in South Africa and in Israel. I know there's a Wuppertal in South Africa and in Germany. Okay, but let's ignore those cases. So let's say we do not accept duplicate node node instances. So we check for that. We get the node, and then we say, all right, if it's null, meaning there is no such node, then we can add it. But if there's already such a node, we cannot add and we ignore. That's what that line 48 says. If there's already a node with this specific value, we don't carry on, we just ignore, we stop execution. Note the difference between small letter u and capital U. Small u is the value of type T. Capital U is the node that contains small u. All right. So note the difference. This is convention. Of course, you can use any variable name. But if we stick to the same convention, it's easier for everybody to communicate on these things. Please don't swap them. Then I will be confused and you won't get your marks. Small letter u is the value that we want to save. Capital U is the node that contains the value. So if U is null, capital U, it means that there is no such node currently in my graph. Therefore, I resize the array, add one element to the array, and then assign my new node to index U underscore. So there's my other convention item. So U is the element with value type T. Capital U is the node in which that element is, and U underscore is the index of that element in the array of nodes. So I create a new node, line 54, and same time that I create the node, I assign it to a specific spot in my array. And that new node that I create gets a value, lowercase u, that will call the constructor in the node, which will assign that value to the node's value. All right, you happy? Can you add a node to a list of vertices? Then if I want to remove a node, that's the algorithm for that. I want to remove a node with a specific value. Go get the node itself with this helper method of mine. If it is null, then there's nothing to do because I cannot remove something that doesn't exist. So if it is not null, I may carry on. If I want to remove a node, I must make sure that I remove that node from all the successors from other nodes. Let's go to the example again. There. If I want to remove, let's say, Webner from this graph, I can travel from Hobbehouse to Webner, from the Westorp to Webner, from Smithfield to Webner, from Zastron to Webner, and from Mafeking to Webner. So Webner is a successor from several other nodes. So I must remove this Webner node from the list of successors from all the others that has it included in its list of successors. I cannot just go remove it. I must first, because next time I remove this and I say I want to travel from Hobbehouse to all its successors, and Webner is in that list, and then sorry, you can't, because this thing doesn't exist. So I must first remove Webner from the list of successors of Hobbehouse, and then only I can remove Webner itself. So this is what we do there. And then I remove the node itself, get the index of it, and this is the normal way of removing an element in an array. Do you remember what we did? Maybe I should just draw this. Where's my pen? I have an array with several cells, and there are values in there. No, you don't laugh. You may not laugh. And I want to remove that one. What do I do to remove it? Well, all that I do is I move that one in there, I move that one in there, and then actually I cut off my array there. Okay? So I just move all the elements up one spot, and then I cut off the element at the end, and that is what we do here. Then I resize my array, meaning the last element is now gone. Resize the array to have one element less. So that's the remove node part. Okay, I'm going to stop there. Just quickly recap. We started off with the idea of graphs, what a graph is. It's not a mathematical graph. Example is a map of towns. I discussed some of the terminology for graphs, referring to nodes and edges and weights and predecessors and successors, etc., etc. I used the word path, I used the word cycle. And then I said we have several possible implementations in which we can model a graph in our programming language. We started off with a model of a list of successors, where we do not save the value, but are just interested in the indexes and the connections between nodes. And I used that as a start off for this discussion on graphs. How to add a node, how to remove a node, and then also in that discussion we referred to a depth first traversal. How to visit all nodes in my graph, and we said that there are two small changes from the depth first traversal from this one that we have from trees. And then we move to the second possible implementation, that is a list of vertices, where we now don't have a two-dimensional structure immediately. We have the two-dimensional structure, but the two dimensions are separated. Of an array of nodes, and then within a node method, within a node class, we have a list of successors. We still have the array of nodes. We still have a list of successors for every node, but they are now separated, which makes it easier to understand in some way. And since we have now an embedded node, we have the possibility of adding a value of type T, and we have the possibility of making the class generic. And then optional, we can also have a list of weights, which will be a parallel list to the list of successors. So the indexes will go the same. This successor, that weight will go the same if they have the same index. And in the weight, we can carry, let's say, the distance from one town to another. So that's my discussion today on graphs. There are still 2 other lectures to come.